So now that we've talked a little bit about rates in problems, the next step is to talk about what's called related rates. Now, a related rates problem is exactly what it sounds like. It's a problem that has two or more rates in it, and it talks about how they are related. So basically, it's usually going to look something like this. It might say like, okay, you got this one thing, and it's changing. It's increasing or decreasing at this rate. And then there's this other thing, and it asks you how fast it is increasing or decreasing. And that's what we mean by related rates. There could be more than two. There could be 3 or 4 rates involved. If there's 3 rates, then basically the problem is going to give you guys 2 of them and ask you to find the third one. But that's what related rates are. They are word problems, and they are a very important part of Calculus 1. So when you guys get to the AP test at the end of next year, you're going to see some related rates questions on that. So here are the steps to a related rates question. I'm going to go through nice and slowly. It's a little bit complicated. But step 1 is to read and understand the problem. And you want to think about how, like right now in the homework, it's going to be easy because you know they're all related rates questions. You don't even have to think about it. But next year when you're taking that AP test, you're going to see those 6 free response questions. You're going to have to read each one and recognize what you're being asked to do. So the first thing I want to do is talk about how you would even know it's a related rates question. And what you want to do is look for rates. We talked about that when we talked about rates. We did one day of notes just on rates. And we said look for things like units. If you see the word per or like miles per hour or cubic centimeters per second, once you see that per, you know it's rates, and it's very likely, not automatically, but very likely a related rates question. So you read this question, you realize it's related rates. The second step would be to draw a picture if necessary. Most of them do require a picture. Some of them you can do without a picture, and some of them the picture will be part of the problem. But if you need to draw a picture, do that. And then assign your variables. So what you want to do is read through the question and figure out what you're talking about, assign variables. You can call them whatever you want, but I like to use letters that represent what it means. Like if we're talking about volume, I'll call it V, or area is A, things like that. Height is H. Now here's a very, very, very important step. As you're assigning variables, you want to stop and think about what things in the problem are constant and what things are changing. Because if something is constant and you assign it a variable, you're going to mess up the problem. You're going to either make it really, really hard to do, or you might even make it impossible to do. You won't have enough information. So it's important to think about that. I'm going to show you an example right now of a kind of a common question. So let's say we have a ladder leaning up against a wall. And that's a common question because it makes a right triangle. But all of a sudden we're going to change it. Let's say the ground is wet and the bottom of the ladder starts slipping this way. So it's actually moving. Well, as the bottom of the ladder slips out, the top of the ladder also slips down. So if you're thinking about your triangle, the bottom of the triangle is not constant. It's changing because it starts out, maybe the ladder started out 5 feet away from the wall. But as it slips, it goes 6 feet, 7 feet. So that would have to be a variable. I would probably call this one X. And the right side of the triangle is also a variable because the top of the ladder is slipping down. So I would call that Y. Now here's the trick. A lot of people go, okay, let's just call this one Z. And that's not the case. The ladder is not getting longer. It's not growing or shrinking. The ladder is a constant. So you definitely don't want to assign that a variable. If you do, it's going to mess up the problem. So what you would do is look back at the problem. Maybe somewhere in the problem it says a 10-foot ladder is leaning against a wall. And you go, okay, well, this is 10. That's not changing. It doesn't matter if the ladder slips down the wall. 10 feet is 10 feet. It's not changing, it's constant. So I put 10 there, not Z. It's very important when you're thinking about assigning variables. All right, once you have your variables, you want to start thinking about rates. And we did a whole day of notes on this. So we said, first of all, look for that per. If you see miles per hour, that's a rate. So find those rates and find what rate you're being asked to find. If it says, how fast is this changing? Or how fast is that changing? Or at what rate is this happening? Figure out what rate you're being asked to find. Then figure out what rates you're given. So once you have those rates, what you need to do is write an equation. This is the related rates part. You need to write an equation that relates the variables from the rates. So let's say, for example, you're reading a question and you realize that the area rate is given. So you say, I have dA dt, that's my area rate. And you're asked to find the radius. Let's say we're talking about a circle. So you're asked to find how fast is the radius change. So you have dr dt. What you need in this problem is an equation that relates a and r, those two variables. So here's another example. It's actually very similar to the one I just did. If you're given dA dt and you're asked to find dx dt, you must find an equation that relates a and x. And again, you're relating this one here with this one here. Now, here's a tricky part, an extra tricky part. It has to relate a and x only. If there's any extra variables in there, you need to find a way to eliminate them. So let's say in this problem, I have area equals, and then I have a function that has both x's and y's in it. So I go, okay, well, I got my equation that relates area, or a and x, but I have this extra variable, this extra y here. Before you can do the problem, you must find a way to eliminate y. You have to have a and x only, or if you look at the yellow ones up on top, you have to have an equation that has a and r only, nothing else. Now, what we've done so far is the hard part of these problems. The rest should be the easy part. So from here on out, you're going to take the derivative of the equation implicitly. That's why we just did implicit differentiation with respect to t. And then it basically just plug some numbers in and answer the question. But like I said, if you've done steps 1 through 5, that's the hard part, turning the word problem into an actual problem. Steps 6 and 7, by the time you get there, you should be kind of relieved. It's just say, oh, okay, finally, this is the easy part. Now I can take the derivative and solve. So let's look at a couple examples. Here's a word problem. It says find the rate of change. So immediately I kind of made it easy on this one. I actually put the phrase rate of change in there. So you can know we're talking about rates, which means it's very likely a related rates question. So we're going to find the rate of change of the area of a rectangle with a width that is twice its length. If its length is increasing at a rate of 0.5 centimeters per second, when it is 10 centimeters long. All right, so step 1, we read and we understood the question. Step 2, let's draw a picture. Now what we're talking about here is a rectangle. And it says the width is twice its length. So what I would do for that is I would put an X for the shorter one and a 2x for the longer one. That's a good way when you're comparing one thing to another, like if it says one thing is 5 times bigger than the other, call one of them x and the other one 5x. All right, so I have my picture. Step 3 was let's name our variables. Well, variables are going to be length and width. It's a rectangle. And step 4, let's get to the rates. That's the real important part. So what we want to find is the rate of change of the area of a rectangle. So let's say we want to find dA dt. Now let's go back and see what was given. What was given is that the length, which is the short one, remember it says the width is twice the length. So this is, in fact, I'll just call it L for now. We'll get the X's later. The length is increasing at a rate of 0.5 centimeters per second. So the given rate is dL dt. It's increasing, so it's positive 0.5 centimeters per second. All right, so now what I've realized here is that in order to answer this question, I need an equation that has A and L only. Well, I know the area of a rectangle is length times width. What I need to do is get rid of that W. This is what I was talking about. So let me change one thing in my picture. Since I'm using L in my question, let's call the length L. And if the width is twice the length, then the width is 2L. And that's how you're going to eliminate W. You're going to substitute 2L right here, because the width is twice the length, it's 2L. So what I have for my equation now is A equals L times 2L, or basically A equals 2L squared. And now I have exactly what I wanted the whole time. Remember, my goal was once I saw those rates, you can see it circled in blue in the bottom left corner. Once I saw those rates, I needed an equation that has A and L only, and that's what I have now. Now, once you have that, we are going to take the derivative with respect to t. So the derivative of A is dA dt. The derivative of 2L squared, we're going to do the power rule. So I multiply by 2, I get 4. I lower the power by 1, I get L to the first power, or just L. But remember, we're taking the derivative implicitly with respect to t. So if I take the derivative of L, I get a dL dt. That's how implicit works. So when you're differentiating with respect to t, you're always going to get a d something dt for any variable other than t, whether it's a or L or x or anything else. All right, now we are about ready to answer our question, actually. So we are asked to find dA dt. We need to plug some numbers in. So we have 4 times L. Now that's when we're going to use this thing right here, this last piece of the equation. That was an extra number that was in there that you might have been thinking, well, wait, where'd that 10 go? That's where the 10 goes. So what I'm going to do is, it says when it, meaning the length, is 10 centimeters long. So I'm going to plug in 10 for L, and I'm going to plug in 0.5 for dL dt, because that was our other rate that we're using. And that's related rates. You're always going to take the one that's given and end up plugging that number in when you're finding the one that you were asked for. So if I just multiply those together, I should have my answer. You end up with 20. And now let's make sure our units are right. You want to do units on these. So we were measuring in centimeters, but this rate is for area. So it's going to be square centimeters per, and then time is measured in seconds. And that's going to be our answer, is 20 square centimeters per second. And you can see these are difficult questions. So you want to really follow those steps we talked about in the notes. Read the question and understand it. Draw a picture. Pick your variables. Pick your rates, and really that's the most important thing. This step that we did down here was the most important thing we did in the whole question, because the rates tell you what to do. Without knowing those rates, you wouldn't have known you needed an equation that relates A and L. All right, let's try one more. Now, water is pouring into a cylindrical, that means a cylinder-shaped tank of radius 5 feet at a rate of 10 cubic feet per minute. How fast is the water level rising? And then I gave you the formula for volume of a cylinder. So let's start with a picture. I'm going to draw a cylinder. Cylinder is like a can shape. And there's some water in it. And there's more water pouring into it. So basically what's changing here, two things are changing. The amount of water in the cylinder, that's volume, and the water level, which is the height. So when I'm naming my, my variables, I'm going to call it V for volume. And I'm also going to call this right here, I'm going to call it H for the height of the water. Now let's go back to the question and pick out our rates. Oh, and also the radius of the cylinder is 5. Now that's a constant. And in part 2, we're going to talk about a very important difference between a cylinder and a cone. A cylinder, the radius is constant, so you just get to plug a number in. On a cone, the radius changes how deep you are. So we'll talk more about that in part 2. Don't worry about it yet. But for a cylinder, the radius is constant. We don't need a variable. We don't need an R. You just use the number 5. All right. Okay, so the water is flowing in at a rate of 10 cubic feet per minute. So first of all, remember I said you can use the units. As soon as you see that cubic feet, you think dV dt. That's volume. So it's 10 cubic feet per minute. And it's positive because the water is flowing in, so the volume is increasing. I could actually give you a similar question where maybe there was a hole in the cylinder and water was leaking out of it, and then dV dt would be negative. All right, how fast is the water level rising? That's H. We called it H, we named that variable. So I am asked to find dH dt. So right off the bat, we got what we need again. We have volume and height. Those are the two rates that we need to relate. Now, let's start with this formula I actually gave you guys. So let's start with the formula. Volume equals pi r squared h. And you say, well, pi is not a variable. That's not a number. I don't have to worry about that. I got my v. I got my h. I need to get rid of this r. Now, in the last example, we got rid of it by using a relationship, like the width was twice the length, so we put a variable in there. Remember what I said, r is a constant. R is just 5. So it's even easier to get rid of it this time. I'm just going to say volume equals pi times 5 squared times h. Or basically, volume equals 25 pi times h. Nice, easy one. And now we're ready to take the derivative. We're ready for that next step. So for the next step, I'm going to take the derivative with respect to t. The derivative of v is dv dt. Now, on 25 pi h, remember, 25 pi is a constant. And h to the first power, remember, when you have something to the first power and you take its derivative, what you're left over is just the constant in front of you. So I get 25 pi. Now I also get a dH dt, but that's kind of the chain rule part of it. But first of all, let's just recognize that when you have 25 pi h to the first power, and you take the derivative, you just get 25 pi. But I do also get a dH dt there. Okay, so let's plug in our numbers. Now this time, I gave you dV dt, so the 10 is going to go here. And to solve, we have one extra step. Last time we just plugged in the numbers, multiplied it out, and we were done. This time we have to divide both sides by 25 pi to cancel that out. And what we get for dH dt is, you can leave it as a fraction. You can also type it into a calculator and get a decimal. It's really fine either way. I'm going to reduce it by 5 and call it 2 over 5 pi. Now for units, it's height, which is a single linear unit. We were measuring in feet, and we were measuring in time in seconds. So for my final answer, I'm going to say 2 over 5 pi, and my answer is in feet per second. All right, just to wrap things up today, here's a couple more volume formulas you might need for the homework. We already had volume of a cylinder. This is a cone and a sphere in case they show up. But basically, I'm going to give you guys a few of these problems tonight to try, and then we'll talk more on part 2.